you begin with the, oops, I need pencil. Okay, begin with the root and two branches, which are careful, and complement to careful is reckless. So careful, reckless. The probability for a randomly selected person to be careful is 0.6, 60%. The other one is 0.4. And there's a 0.3 probability for careful driver to be in an accident. That means accident happening, given driver is careful. Careful driver, accident happening is 0.3. So that probability is 0.3. And so 0.7 probability for no accident, complementary. And reckless driver having accident, probability is 0.4. 0.4, and no accident, 0.6. Okay, so now we can find the probability for the end of the branches. So this probability at the end of this branch will be accident and careful intersection. The probability that the person will have accident and he is a careful driver. That would be equal to, so let me write down the detail. Probability for careful driver intersection accident equal to probability for accident given careful driver times probability for careful driver. So in other words, I need to multiply this probability by this probability. 0.6 times 0.3, 0.18. So 0.18 is the probability at the end of this, which is equal to C intersection A. This is probability of C intersection A bar. No, A intersection C bar. Sorry, C intersection A bar. Complement of accident. In other words, no accident. No accident given careful. That's what 0.7 is. So the product of these two will give you the probability for both to happen. So 42. 0.42. And similarly, this product for 0.4 times 0.4, 0.16. And this is 0.26. Yeah, 0.26. Now let's go to the question. What is the probability that randomly selected driver will have an accident within a year? So that means probability to have an accident. So this here we found probability for accident given careful driver. And here we have probability for accident given reckless driver. So probability for accident equal to probability for accident intersection careful driver plus probability for accident intersection reckless driver. We did that in the last class. So basically all the branches where the accident is, you need to add them up to get the probability for accident. So accident given careful, accident given reckless have to be added up to get the probability for accident. So that will be equal to 0.18 plus 0.16. So that's the probability for accident. And if the question is, what is the probability that there will be no accident? For the randomly selected person, there will be no accident. That would be 0.42 plus 0.26. So this is the key. You have to add up the accident intersection, both cases. All right, anything else?
Number 8.
8, okay. Three people are selected from a group of 6 men and 4 women. Find the following probabilities. First one is all three. First one is all three are men. Second one is first two are women and the third is a man. All right. So the first part is just a regular question. It doesn't have any conditional probability in it. So let's see, 6 men. 6 men and 4 women are there. And we are selecting 3. So count of the sample space is number of ways of selecting 3 from 10. There are 10 people altogether. So C combination 10 comma 3 equal to factorial 10 over 7 times 3 equal to 10, 9, 8, 3, 2. 3 divides 9 into 3, 2 divides 4, 12, so 120. Going over to the event. The event in the first case, part A is all 3 men. All 3 men. That means all of them have to come out of the men. So the number of elements in this event is combination 6, comma 3. Okay. That will be 6 times 5 times 4 over 3 times 2. 3 times 2 is 6, so 20. So the probability is for E is 20 over 120 equal to 1 over 6, which is equal to 0.16666. Part B is probability that the first 2 are women and the third is a man. Okay, this can be done 2 ways, using counting technique like I just did for the first part, or by using conditional probability. So let me do it by conditional probability. Probability for first 2 women, 2 women, or first 2 women. Well, we'll keep that in mind. This refers to first 2 women. And the second, and the third is man. Third is man. Is same as probability for man given first 2 women times probability for 2 women, first 2 women. All right, so probability for the first 2 women would be combination. I'll just write combination, you know how to simplify. There'll be 2 have to come from the women, so there are 4 women, so that will be combination 4, 2 divided by selecting 2 from first 2 will be women. So the question here is, what is the probability that the first 2 will be women? So that means you're selecting 2 from 10, and those 2 have to be women. So C42 is the numerator, and C102 will be the denominator. You're selecting 2, and the both of them have to be women. And this part is, given first 2 are women, what is the probability that the third one is a man? So first 2 are women means 2 women have been selected already. So you're now selecting 1 person from the remaining ones. And the remaining ones are 6 men and 2 women, 8 people altogether. So C8, 2 in the 8, 1. You're selecting 1. 8, 1 in the denominator. And that one has to be a man means he has to come from 6. All 6 men are there because the first 2 were women. So given first 2 were women means all men are there. So the number of ways of getting 1 man from the men would be C6, 1. From the 6 men, 1 has to come out of it. But the denominator is C8, 1 because you're selecting 1 from all 8 people. So a number of ways of selecting 1 person from all 8 would be the sample space in this case. And C6, 1 is the number of ways to get 1 man from, there are 6 men, so the number of ways to get 1 man is C6, 1. So simplify that to get the answer. Yeah, that'll be it. All right, so we don't have any more time for the discussion.
Sir, how did you get C81 again? I'm sorry.
Okay, so the whole thing is now broken up into taking 2 first, okay, and then taking 1. Two people have to be, say it says first 2 have to be women and third has to be man. So that's why we have this second part, 2 women, probability for 2 women part has to be done first. That would be, if you select 2 people from the 10 people, what is the probability that both of them are women? That's what that part is. So from 10 people, you're selecting 2. So C10, 2 is the sample space. And both of them have to be women means they have to come out of the 4. So 2, C4, 2 is the numerator. Now the other part is, after selecting 2 women, if first 2 have been women, what is the probability that the third one is a man? So after selecting the 2 women, now you're selecting 1 man, 1 person, and that has to be man. So selecting 1 person means number of ways of selecting that 1 person will be C8, 1. There are only 8 people left. 2 people have been selected already, and they are women, right? So there are 8 people left, and you need to select 1. And so this is how many ways are there to do that. And then number of ways of selecting a man would be C6, 1. There are 6 men. All 6 men are there because the first 2 were women. So a number of ways of selecting 1 man from the 6 men would be C6, 1. So that's,
Okay, thank you so much.
so this is the count of event. This is the count of sample space. All right.
Thank you.
If we have more time, we will, we can come back to the discussion of the homework. But I have to get to the handout, the worksheet. So let's go to the worksheet. All right, so we are doing independent events and applications. So I need to explain to you what independent event would be. All right. So let's begin understanding what independent event is. I'm going to start with a simple example of drawing card. Now we did so many problems of drawing card with conditional probability, but this one is slightly different. I draw 1 card from a deck and observe the outcome, and I put the card back. And then they shuffle the deck and take another card. And the problem says, find the probability that the first card is ace and the second card is king. First card ace, second card king. All right, so that means we need probability for king second and ace first, both. So that's the intersection. That's equal to probability for king second given ace first times probability ace first. This is how we have been doing it. Nothing wrong with that. We can still use that. But the only difference is the probability that the second is king given ace first is same as just probability of king. Why? Because first card was A's or not, you have put it back. So if you put it back, then what the first card was doesn't matter for the second card, right? It doesn't affect what happens to the second card. Only if the first card was not put back, then one card is missing. So you have only 51 cards. And if the first card was king, then you have one fewer king. So the probability will depend on what that card is. But if you put the card back in, the probability of the second card being king doesn't depend on what the first card was, right? So that's what independence means. Now, since you have put the card back, probability for the king second given first, given ace first, is same as probability for king second. It doesn't depend on ace. Whether the first one was ace or not doesn't matter. And so the probability simply is 4/52 for the probability to be for the king, for the second card to be king, given first card is ace, is same as the probability for the second card to be king, period. You know, it doesn't, because ace, first card was ace or not, doesn't affect it. There are still 52 cards and 4 of them are king. So 4/52 is your probability for that part. So therefore this first part is 4/52 and probability for ace is also 4/52, right? First card to be ace, 4/52. So the probability for the entire problem is probability of king given ace is 4/52. Probability for ace first is also 4/52. So the answer is simply this. So you can still use that formula, but the only difference is the king, whether king is second, getting a king second doesn't depend on what was first card because you put it back. So when this happens, we call them independent events. In other words, the king second and ace first are independent events when you put the ace back. When you put the first card back, those two events are independent. So that's a simple example of independence. And so let's see, we're going to learn more about independence and then we'll do some more examples. So if we say E is independent of F, if probability of E given F, now E is independent of F means E doesn't depend on F, which means E happening given F happens is same as E happening given F has happened is same as simply E happening. It doesn't depend on whether F has happened or not. Now the other way around is F is independent of E means F occurring doesn't get affected by E occurring, which means F given E is same as E F, doesn't depend on E. So F is independent of E means F is not affected by E, which means F happening given E happened is same as F happening, doesn't depend on E. And E independent of F means E given F is same as E, doesn't depend on F. So that's the meaning. Now, the next thing we need to understand is we already know this formula probability of, let me put that on the next slide. All right, this formula we already know from the last chapter. Probability of E intersection F is equal to probability of E given F times probability of F. We call this the multiplication rule. Some books will call it product rule. Doesn't matter. It's one important rule in conditional probability. And now look at this formula. And what happens if E is independent of F? If E is independent of F, then this part is equal to probability of E, right? Probability of E given F is same as probability of E. So therefore, this formula takes this form. Probability of E intersection F equal to probability of E times probability of F. So that happens if E is independent of F. Okay, so now I'm going to show you why if E is independent of F, then F is going to be independent of E. It's going to go both ways. I'm going to show you why mathematically. So let's on the board now. I'm gonna. It's all worked out on the worksheet here, but I'm gonna write it on the board. So let's assume now that assume E is independent of F. That means probability of E given F is same as probability of E. Okay, if that's true, then probability of E intersection F equal to probability of E given F times probability of F, which takes the form probability of E times probability of F. So I just showed you why. So it takes the form probability of E times probability of F. The multiplication rule takes that form because they are in, E is independent of F. So now we have this, and now the next thing I want to show is F is independent of E. To show that, I need to show probability of F given E is same as probability of F. That's what I need to show. So let's take probability of F given E and apply the formula. We have a formula for the conditional probability, which is F intersection E divided by probability of E. But we already have probability of F intersection E, same as E intersection F, equal to this. So let me put that in place of this intersection. So that'll be probability of E times probability of F, right? Intersection. For the intersection, I'm putting this. Divided by probability of E. So you can see that these two cancel out to give you probability of F. I just proved that probability of F given E equal to probability of F. In other words, if E is independent of F, then F is independent of E. See, F given E is same as F means F doesn't depend on E. So F is independent of E. I just proved it. So if E is independent of F, F is independent of E. So therefore, if any event is independent of the other, we can simply say they are both independent of each other. They are always, if one is independent of the other, then they're both independent of each other. So that makes it less complicated. It makes things easier. So if E is independent of F, then F will be independent of F. So we can simply say they're both independent of each other. So here is the fact we just discussed. Event E and F are independent if and only if this is true. We can go backwards too. So we just proved that if E and F are independent, then this formula is true. And if this formula is true, then they are independent. Why? In other words, the opposite statement is true. And I'm going to show you why. So this is given to you, probability of E intersection F equal to probability of E times probability of F is given. I want to show that if this is true, then E is independent of F. To show that, I need to take a look at probability of E given F and show that this is equal to probability of E. Okay, I'm going to show you that. I'm going to apply the formula for the conditional probability, which is E intersection F over probability of F. And now we know that this is true. So therefore, I can replace the E intersection F with probability of E times probability of F. So the F part cancels out to give you probability of E. So I have just proved that probability of E given F is equal to probability of E when this is given. So that means if this is true, then E is independent of F. We already saw earlier that if E is independent of F, then F is independent of E. So therefore, when this is true, E and F are independent. So we have the statement going back and forth. If E and F are independent, then this formula is true. And if this formula is true, then E and F are independent. So therefore, that's when we say, we make this statement this way. Event E and F are independent if and only if probability of E intersection F equal to probability of E times probability of F. Okay, so in the problems, when in the problems you're going to do, some of them will ask you to prove that the two events are independent, or verify that they are dependent. So you can use one or the other method. You can either verify this, E given F same as probability of F, probability of E, or F given E is same as F, or verify that this is true. Choose whichever is convenient for the specific problem. Feel free to interrupt me if you have questions. So we're done with the theory, and we are going to proceed to do some problems. Probability of E is given, F is given, and it says E and F are independent. It already tells you that they are independent. And let's answer these questions. First question says, what is probability of E given F?
0.6.
0.6, very good. Because E is independent of F, means probability of E given F is same as probability of E, and therefore equal to 0.6. Okay, F given E.
0.2.
0.2. Very good. And probability of E intersection F.
0.12.
0.12, 0.6 times 0.2, because we just learned that if the events are independent, then probability of intersection is same as product of the two probabilities. So 0.6 times 0.2 is 0.12. Okay, going on to 12.3. Probability of E is given, F is given, and intersection is given. Are these events independent? So which method is convenient here?
Multiplying the probability of E times the probability of F.
Right, that is the convenient, this formula here. We can check that. Okay, 0.3 times 0.2 is equal to 0.06. 0.06, but E intersection F is 0.6, so they're not equal. So they are not independent.
Aren't they independent? It's 0.3 and 0.2.
Yeah, but 0.3 times 0.2 is 3 times 2.
No, they're not independent.
6 with the 2 decimal digits. There are 2 decimal digits in the answer, so it's 0.06. Okay.
Oh, okay, thank you.
It's not 0.6. I know it's easy to make that mistake. If you don't see it, you can use calculator. You're allowed to use calculator. So multiply them. It's 0.06, which is not equal to point intersection. Okay, now this one, next one says probability of E is 0.4, probability of F is 0.5, and events are independent. Find the probability of E union F. All right, where do we begin? Anybody?
We wouldn't add point E and point F and subtract it by 1, right?
Where are you getting the 0.1 from?
Not 1, I mean just 1. Add 0.4 and 0.5 and subtract it from 1.
Where are you getting that from? That's on I think you're thinking in terms of mutually exclusive. Even if they're mutually exclusive, the complement of the union is what you're finding. The question is probability of the union, not complement of the union.
So
Yeah.
to find out, we would add the 0.4 plus 0.5 and take away 0.2.
Where are you getting the 0.2 from? The
The
product.
intersection.
Okay, so that's you're right. And so my question was, where do I begin? So basically, you're saying I should find the intersection, right? Is that what you're saying?
Yes, that's what I said.
Yes. And equal to
0.2.
0.4 times 0.5, which everybody's following me. Since they're independent events, probability of E intersection F equal to probability of E times probability of F. Yeah, you got it. Ari, Pasha, you got the right way, which is good. So 4 times 0.4 times 0.45, 0.5 will be the intersection because they are independent. Because they are independent, we have this fact: probability of E intersection F is same as probability of E times probability of F, and that's what I'm using. So the product of those two probabilities will give you the probability of the intersection, which is equal to 0.2 and 0.4, 0.5, 20. Yeah. So now we can apply the union rule. Probability of E union F equal to probability of E plus probability of F. She was doing all that in her head. That's what happened. So minus probability of E intersection F. Okay, so probability of E is 0.6. Probability of F is 0.2 minus probability of E intersection F is also what? No, I'm mixing up the numbers somewhere. Where am I? Yeah, here. E is 0.4, F is 0.5. 0.5 minus intersection is 0.2, and so 0.9. So I had to use the union rule to find the union, E union F. All right, so let's go to the next one. 12.5, it says the Venn diagram shows the number of elements. So in the Venn diagram, we see the number of elements of each section. And we can add up everything to get the sample space. And that's 20 plus 20, so 100. There are 100 elements in the sample space. So now we can answer the questions. Are E and F mutually exclusive? What's your answer?
No.
No, there is an intersection. So when there is something common to them, both events can happen at the same time. So therefore, they're not mutually exclusive. Find probability of F given E and F and probability of F and determine whether or not E and F are independent. Okay, so we can find F given E and probability of F to verify, to determine whether they are independent or not. So I'm doing that on the board. Probability of F will be number of elements in F, which is 25 over 100. 25 over 100 is the probability of F, which is 1 over 4. Probability of E, they want F given E, okay. F given E means E has occurred. So if E has occurred, then you're limited to the circle E. And now, what is the probability for F to occur? Anybody?
5 over 15.
5 over 20.
Yeah, 20.
5 over 20. Because E has occurred means now you're limited to the circle E. So the universal set has 20 elements, all the elements in E. And the only way F can occur now is if the actual outcome is in the intersection here. If only if it is here, F can occur. So therefore, 5 over 20. Now, this is not first time we are doing this. We did this before, except the independent events. We did find probabilities of conditional probabilities from Venn diagram before. So it's 5 over 20, which is equal to 1 over 4. So you can see that probability of F given E and probability of F are equal. So therefore, Independent is the conclusion. They are independent. Okay, and then the next exercise says, we found that E and F are independent, so verify that E intersection F has the probability of E and probability of F. So the multiplication rule for independent events can be verified now, and that's what it says. So let's find probability of E intersection F, and that's 5 elements are there in the intersection. So it's 5 over 100, and probability of E is 20 over 100. Probability of F is 25 over 100. 25 over 100. So probability of E times probability of F is 20 over 100 times 25 over 100. Okay, 25 divides 100 into 4. 20 divides 100 into 5. So it's equal to 1 over 5 times 4, 1 over 20. And this is also 1 over 20. So they are equal. All right, moving to 12.6. The Venn diagram shows the number of elements in the sections. Are E and F mutually exclusive? What's your answer?
Yes.
Yes. There is nothing in the intersection means they cannot occur at the same time. So if E occurred, F cannot occur. If F occurs, E cannot occur. So when a situation like that, when the situation has such separate circles for the two events, what happens to the conditional probability? Find probability of F intersection, F given E.
I'm sorry, can you explain how you got 4 in the last example?
Which 4?
4 over 20.
4 over 20. Where are you?
For exercise 12.1.
12.1, okay. Probability of E intersection F was 5 over 100. You understand that, right?
Yes.
Okay, there are 5 elements in the intersection. 100
About the probability E times probability F at the bottom.
Okay, probability of E times probability of F is 20 over 100 times 25 over 100. And then I'm reducing the numbers that reduce. The 25 divides 100 into 4. Right? There are 4 hundreds in 4 25s in 100.
Okay.
And there are 5 20s in this 100.
Okay, so it was actual cross multiplication that occurred. Okay.
Yeah, exactly. You're multiplying 2 fractions, so you can, there are 2 hundreds in the denominators. It's basically this, 20 times 25 over 100 times 100 is what you have. So you can reduce them in any way you want. 25 reduces this 100 into 4, and 20 reduces this 100 into 5. Okay.
I was just confused because when we did fractions before, we kind of like flipped the fractions and we would then.
That's if you're dividing. If I'm dividing 20 over 100 by 25 over 100, then that's same as 20 over 100 multiplied by 100 over 25.
Okay, I got it. Thank you.
Okay, so let me clear that screen. So going over to the problem 12.6, are E and F mutually exclusive? Yes. So let's find probability of F given E. F given E means E has occurred, and we need the probability of F. E has occurred. So if E has occurred, you're here in this circle. What is the probability for F happening? Anybody?
0.
0. Because there is nothing in common. So if E has occurred, you are in the E. Your outcome is in here means it cannot be in F. There is no way you can be in F if you're in E. only if there is something in common, like this. If you're in E, then there is 0.2 probability that you are in the F as well, right? When there is intersection, you can be in F when you're in E. But when there is no intersection, if you're in E, you cannot be in F. So therefore, probability of F given E is 0. What is the probability of E given F?
0.
0 again. Very good. So are they independent? No, because
Yes.
probability of E is not 0. See, for them to be independent, probability of E given F must be equal to probability of E, right? Only then they are independent. But probability of E is not 0, it's 20 over 100, right? This is 20 over 100, but F given E is 0, or E given F, both of them are 0, right? So they're not equal. So they're not independent. You know, you can think in terms of, you know, the fact. If E occurred, then F cannot occur, means E is affecting F, right? If E has occurred, then F cannot occur. So that means E is affecting F, right? So it's not independent. They are independent only if one doesn't affect the other. Here, one affects the other. Just without doing math, if you just think about it, if they are mutually exclusive, then if E has occurred, F cannot occur, which means E is affecting the F. So they are not independent. All right, going on to 12.7. The Venn diagram shows the probabilities of the sections. Determine whether E and F are independent or not. Okay, which method do you want to use? We have two ways to do that, right? One is to find E given F and compare it to E, or F given E and compare it to F, doesn't matter. And the other one is the product rule for independent events. So either way is going to be fine. You can do it either way. So we can find probability of E first. What is probability of E? Anybody?
0.5.
0.5. You have to add the 0.3 and 0.2 to get the probability of E. And probability of E given F would be what?
0.2 over 0.6.
Point E given F, F has occurred, yeah, 0.2 over 0.6, right? So 0.2 over 0.6. So let's simplify 0.2 over 0.6, and that's equal to 2 over 6, equal to 1 over 3. And 1 over 3 is same as 0.333, so that's not equal to 0.5. So they're not equal. So therefore, not independent. Not independent is the conclusion. So there are some questions in your homework that says determine whether the events E and F are independent or not, and they have two answers in multiple choice: independent, not independent. So clearly, you have to finish. You have to get the answer right in one attempt. You know, obviously. So in such problems, there's only one attempt given to you. All right, 12.2 says study of 60 students who took math and science courses revealed that 20 received A in math. All right, I'm going to put Venn diagram. Clearly that calls for a Venn diagram. A in math, that's what this event is. And that is 20 students are there, 20 students. And the other one is 30 received A in science. I'll just call it S, A in science. I'll call A in math as M. 30 received A in science, okay? 10 received A in math and science in the intersection. 60 students altogether took the test. So 60 in the sample space. Determine whether the events received A in math and received A in science are independent or not. Okay, received A in math, that's this event. So probability of, to determine whether they are independent or not, I need to find, let me find the numbers in each section. 10 here and 20 here and 20 plus 20, 40, so 20 outside. To determine independence, I have to do math given science. A in math, that's what this means. Given A in science, and show whether this is equal to probability of M. That's the question, right? Is it equal to that? So let's find probability of M first. Probability of M is 20 over 60. 20 students got A in math out of 60. So 20 over 60. And M given S means S has already occurred. So you're here means you're limited to 30. And only way M can happen is if you're in the intersection. So 10 over 30. Okay, 10 over 30 is equal to 1 over 3. This is equal to 1 over 3. And this is equal to 1 over 3 as well. So they are equal. So you really have to calculate them and check them. They are equal and therefore they are independent. Going on to 12.3.
Professor, can you go over that for me, please? I got lost at 20 over 60.
20 over 60. Okay.
Yeah, I don't know how we got 20 over 60. I was lost over there.
All right. Probability of M is this set right here, right? And there are 20 elements. Agree? 20 elements. 20 people have received A in math. And 60 is what we have in the sample space. So probability of this event is number of elements here, which is 20 over 60. Okay.
Yes, I see that.
All right. You understand the other part? M given S?
No, I don't.
Okay. Probability of M given S means S has already occurred. That means you're now here. So you're limited to these 30 elements. There are 30 elements here. So that 30 is your denominator. Out of those 30, how many elements will make the M happen? These 10.
Oh, 10.
Okay. We have been doing this many times, finding conditional probability from Venn diagram. So these 10 out of 30. So 10 over 30 is the probability for that. Okay. If you need further help with that, you can stay after the discussion. All right, so let's go on to at the end of class. I can explain again if you like. 12.3 says a box of 12 bulbs include 3 defective, and we are taking 2 bulbs without replacement. Then E is first one is defective, F is second one defective, and are they independent is the question. All right, so to determine the answer to that, we need to find one of the conditional events or find the intersection and show that it's equal to the product, either way. So maybe we'll do the intersection method. The first one defective, the E is first one is defective, F is second one is defective. So let's find the probabilities of E and F. Probability, let me write down the numbers first. The 12 bulbs include 3 defective. So there are 3 bad ones, 9 good ones. And we are taking 2 bulbs. So count of the sample space will be number of ways to select 2 bulbs from 12. So C 12 2. And then let me see if I can quickly simplify that. Over 10 factorial times 2 factorial equal to 12 times 11 over 2, 6, so 66. That's the number of elements in the sample space. And the event E, count of E, first one is defective. So we are selecting two, and we want the probability for the first one to be defective. That means one defective, one good. First defective, second, wait a minute. First one defective means the order matters. So, they're talking about first and second, so the order matters now. So I have to use permutation. So sample space, I had to do the sample space again. Okay, sample space is permutation of 12 comma 2, and that will be factorial 12 over factorial 10, which is equal to.
So it's not combination, it's permutation?
Because we are talking about first one defective, second one defective. So it's the order matters now. So we have to count all of the ways of selecting 2 and rearranging them. So that's why the number of elements in the sample space is all the ways to have 2 of them selected and rearranged. All those, because the order matters now. Okay. So it's permutation now, not combination. If the question is like, instead of asking first defective, second defective, if it says, what is the probability that we are selecting 2, what is the probability that 1 is defective? That means order doesn't matter. You have 2 and one of them has to be defective. Means you're not, the order doesn't matter. But the question says, what is the probability that the first one is defective? So first one defective, second one non-defective. They had to be in that order, right? So that's when order matters. So when the order matters, you had to count all of the rearrangements in your sample space. So it's 12 factorial over 10 factorial, which is equal to 12 times 11. That's 132. That's how many elements are in the sample space. And number of elements in the event will be, first one is defective, second one good. You're selecting 2, and first one has to be defective and second one has to be good. So how many ways can I put can I get 1 defective from the 3 defective? 3 ways, right? Now I am using box method. The first one has to be defective. There are 3 ways to do that. There are 3 defective ones. Second one has to be good for the event E. The event E says first one is defective. We are selecting 2. So first one defective means second one good. That's what it means. So 3 for select number of ways of selecting 1 good is 1 bad is 3. And the other one has to be good. So that's 9. So 27 ways to get first one defective, second one good. So therefore, probability of E is 27 divided by 132. Similarly, count of F is second one defective, means first one has to be good. So now, since they are 1 and 1, I can easily use box method. First one has to be good, second one has to be defective. So 9 ways to do the first one. And yeah, it's going to be same. 3 for the second one. So 27 again. So the probability for that also, that is same as the other probability, 27 over 132. Our question is independent. So we have to find probability of E intersection F. E intersection F would be first one defective and second one defective, right? And that means both have to be defective. To find that, I need to find count of elements in E intersection F. Count of elements in the event of getting both defective. Okay, they have to be both defective, and there are two of them. So the number of elements, number of ways of getting both defective is number of ways of selecting two from 12. I'm sorry, not 12, 3 defective. So from 3. So that would be C3, 2. Now, since they are both defective, the order doesn't matter. They're both defective. So C3, 2 is factorial 3 over 1 times factorial 2. So that's 3 equal to 3. So probability of E intersection F is 3 over 132. So probability of E intersection F is not equal to the product of the two probabilities of E and F. So they're not independent. You can also do it the other way. The E given F, you find E given F and then find and show that it's equal to probability of E. Or if it is equal to probability of E, then they are independent. Otherwise, they are not independent. All right. Now, determining independence by common sense.
I have a question.
Yeah.
How we were using permutation to find sample space. Why did we transition into combination to find the intersection?
Because in the intersection, they're both defective. So first defective and the second one defective means now, see, if I take two bad ones and rearrange, that's not a different one. They're both still bad, right? So when they're both bad, the order doesn't matter. When the one is defective, well, the other one is good. It says first one has to be defective, second one has to be good. So that there, the order matters.
I understand now, just because we're just focusing on the bad now.
Yeah, so now we have both defective, so rearrangement is not a different one.
Thank you.
Going on to independence by common sense, you know, sometimes we can tell whether two events are independent or not just by using common sense. We need to understand that next. So let's look at the event. Student passed psychology class, and the same student is taking chemistry class. So one event is student passed psychology class, the other one is student passed chemistry class. Are they dependent on each other? Clearly not, right? Two different classes. Whether you pass psychology or not doesn't affect whether you pass chemistry or not. So they are independent events. Here's the second example. Two men, John and Jacob, are throwing darts, and John hits bull is one event. Jacob hits bull is another. They're clearly independent. They're two different people. So whether one hits bull or not doesn't depend on the other. All right, 12.5 says a die is rolled twice. Determine whether the following events are independent, mutually exclusive, or neither by using common sense. E is rolling, first rolling results in 5. F is second rolling results in 6. So are they mutually exclusive? first one results in 5 means the outcome of the first rolling is 5. Now you're rolling again, second time, you're getting 6 in the second one. So can they both occur at the same time or not?
No?
Yes, they can.
They can. The first one, getting a 5 in the first one and getting a 6 in the second rolling is possible, right? Getting both. You're rolling once and you can get 5, and then you're rolling again, you can get 6, right? So they can happen at the same time. So they're not mutually exclusive. They can happen at the same time. Now, are they independent?
No,
Why?
because they can depend. If the first one is gonna be 5, then the second one might be 6.
In other words, to determine independence, you had to think about whether one affects the other or not, right? So if I get a 5 in the first rolling, does that affect the chance of getting 6 in the second rolling?
No,
No. Second rolling is completely independent of the first rolling. What I got in the first rolling doesn't affect what I get in the second roll. Agree with that?
yeah,
Yes, so they are independent. So you really have to think about it, whether one affects the other or not. And these two don't. For the mutually exclusive, you need to ask the question, can they occur at the same time? Getting a 5 in the first roll and that's getting a 6 in the second can occur at the same time. So you can get a 5 in the first rolling and get a 6 in the second rolling. It's possible. Okay, 12.6. Tom and Mary are taking the same math course. Determine whether the following events are independent or mutually exclusive or not. Tom passes the course, Mary passes the course. These are the two events. First of all, are they dependent or independent?
independent.
Independent, because Tom passing the course doesn't affect Mary passing the course. And are they mutually exclusive?
No.
So the question you ask is, can they occur at the same time? Yes, right?
Yeah.
So they're not mutually exclusive. They both can pass, right? So they're not mutually exclusive. Now it says Tom has 0.6 chance to pass the course. Mary has 0.7 chance to pass the course. What is the probability that they both pass? Anybody?
0.6 times 0.7.
0.6 times 0.7.
0.42.
Yes, exactly. Because since they are independent, we already know by common sense they are independent. So therefore, probability for both to happen, Tom to pass and Mary to pass, equal to probability for Tom passing times probability for Mary passing. And so just multiply them to get the answer. Example 12.8 says, Jake and Kyle are shooting at a target, when the probability for that each one will hit the target is 0.4 and 0.6. Find the following probabilities. Probability for both will hit the target. What is it, anybody?
0.4 times 0.6.
0.4 times 0.6. Part B is both will miss the target.
1 minus 0.24.
No, that's you're finding complement of both hitting, right?
Yeah,
Both hit the target.
Wouldn't you have to find what's outside of the intersection in the two circles?
Yeah, but you don't have to go that far. See, basically what we are trying to find is probability for complement of T, Tom failing to hit the target, right? Oh, Jake and Kyle, sorry. So probability for Jake not hitting, I'll call it J bar, and probability Kyle not hitting target. So J bar intersection F K bar. That's what we're looking to find. And they're also independent because Kyle hits or not doesn't hit, or Jake hits or doesn't hit, are totally independent. So therefore, this will be equal to probability of J bar times probability of K bar.
I think the answer is 0.24.
Yeah, 1 minus 0.4. J bar is 1 minus 0.4, which is 0.6, and that's 0.4. So it's going to be same answer as
But
this.
I didn't do it like that. I don't understand the way you did it, really.
Okay, do you understand this? Probability of both missing the target means Jake should miss, right? That's complement of Jake hitting the target, right? That's why that's J bar. And Kyle should miss, that's the same as complement of Kyle hitting the target. That's why it's K bar. Okay, and we want both to miss means J bar and K bar should happen, intersection. Are you following me?
Yes, Professor.
Okay, so that would be, since they are independent, the product will give you that probability. So multiply these two. Part C, one hits the target and the other misses. So probability for Jake to hit the target and the other one to miss. So probability for Jake to hit and the other one to miss is this. So since it says one hits the target, the other misses, it can be Jake hitting, Kyle missing, or the other way around. So I have to say this, Jake hitting it and Kyle missing it, which is this, union, Jake missing it, Kyle hitting it. So that's what I need. So the probabilities will have to be added because of the union. So probability of this and probability of this have to be added. And probability of this, the probability of this equal to probability of J intersection K bar. That'll be J is 0.4, K bar is also 0.4, 0.4 times 0.4. And probability for J bar is 0.6 and K is also 0.6. So 0.6 times 0.6, and you need to add them. All right, what I need to, so we are out of time. All you need to know is this. The probability rule that we learned here extends to 3 events as well. Probability of E intersection G, E intersection F intersection G equal to E given F intersection G times probability of F given G times probability of G. This is the formula, but you don't really have to memorize this because I'm not going to give you a problem on 3 events intersecting, except for independent. If all 3 are independent, then these conditional probabilities are, this conditional probability is same as probability of E because it doesn't depend on F or G. And this is equal to probability of F. And therefore, if 3 events are independent, then probability of E intersection F intersection G is same as product of all 3. The same thing we learned for the 2 events apply to 3, even for multiple events. Even if you have 4 events, 5 events, if they are independent, then the probability of all of them happening is equal to product of the individual probabilities. So that's basically what you need to take out of that. So see here is yeah, go ahead.
Do we have any questions on the homework based on this?
Not on that formula. So yeah, I was going to explain that just for the sake of understanding, but I didn't want to give you problems on that. That's a little bit too complicated. If I give you an application problem on that, which is what I have here next. This is an application problem on that, but I don't really want to give you that. That's a little too complicated. That's a little bit beyond this course, the limit of this course. But you do need to understand how to do them when they are independent. So here's a simple example. 3 policemen are shooting at a target. The probability that each one will hit the target is 0.4, 0.6, and 0.7. Then what is the probability that all 3 will hit the target? That's just the product of those, right? So similar to before. Okay, so that's basically all you need to know in this part. I already told you it extends to any number of events. The same thing extends to any number of events. That's all we need to know here. So the only thing I didn't explain is how this works, and that I wasn't planning to give you any problem on that in your homework or test. So it's a little bit too complicated for this class. All right, so that's all there is today, and the homework is already up. And everything we have done will be on the test coming up on Wednesday next week. So you need to do the practice test. I think I may have
When would the practice test on WebAssign be uploaded?
not yet. I'm not even sure whether I'll have one or not, but if there is going to be one, it will appear sometime later today. Okay. But the printed one, you have to really rely on mostly to practice for the test. I may have a couple of problems on the base rule. I have decided not to have the base rule for the exam, but we will do it after the exam. So if I have any question on that topic in the practice test, then you don't have to do them. If there are, then they will be last 102. And I will send a message to ignore those problems. I think there are 102 at the end. But base rule is not going to be on the test. So the entire probability will be on the test. So everything we did after the first test will be covered by this test, but nothing directly on the first part. But everything you learned in the first part applies here, like the counting techniques, all those apply here. So you do need to know them, but there will be no direct questions on them. The questions will be all on probability.
And the math exam will be next Wednesday or next Monday?
Next Wednesday. And Monday, I will take questions on the practice test. And also, if I actually post a practice test on the WebAssign, then you can bring up questions on that also. So the next class is going to be pretty much discussion of the practice test to prepare for the test. And following class will be test. Okay?
Thank you, Professor. Have a good day.
You're welcome. Everybody have a nice day and nice weekend too. I'll see you Monday.